Today we will be discussing velocity and particle motion. This concept uses derivatives, second derivatives, and their graphs to understand particle motion. Derivatives are vital to understanding particle motion, thus calculus is necessary in this process. The first word to know is displacement. Displacement is the position of a particle over some time interval. To find displacement, use the equation above. Velocity is the rate of change of position with respect to time. Speed is the absolute value of velocity. The difference between speed and velocity is that velocity has a direction, while speed does not. Acceleration is how quickly the velocity is increasing or decreasing. There are two main equations associated with velocity. The first is the equation to find the average velocity. To find the average velocity, use displacement over the change in time. The second equation is to find the instantaneous velocity. The equation listed above uses limits, but you could also just find the derivative of the equation f of t and then plug in your time value. We will now discuss how to evaluate velocity and particle motion using a graph. Above is a graph of f of t. This graph shows the displacement of a car. We will use this graph to answer several questions. The first question is, what was the initial velocity of the car? The initial velocity of the car was 0, because at 0 seconds the car had moved 0 feet, and the derivative at 0 was 0. The next question is, was the car going faster at A or B? The answer to this question is that the car was going faster at A. This is because at A, the slope of the line was greater than it was at B. To find the velocity, one could look at the graph of the derivative, or you could just look and assume that at A, the slope was steeper than at B, because that's what you can visually see on the graph. The next question is, was the car slowing down or speeding up at A, B, E, and F? To answer this question, you must visually picture both the derivative and the double derivative. The derivative represents the velocity of the car. The double derivative you can use to see the acceleration of the car. When both the velocity and the acceleration have the same sign, then the car would be speeding up. But if velocity and acceleration had different signs, then the car would be slowing down. Based on this, we can see that the car was speeding up at points B and F because the graph of both the velocity and the acceleration both had the same sign. But at points A and E, the velocity was the same, showing that the car was not speeding up or slowing down, rather going at a constant rate. None of the points were slowing down. This is because at none of these points were the signs of the acceleration and the velocity opposite. The final question is, what is happening between C and D? The answer to this question is that between C and D, the car is stopped. This is because between points C and D, there is no change in position, meaning that the car has not moved. The next problem that we will look at is a graph of the velocity, or a derivative graph of the position versus time graph. The graph below gives velocity function of a particle that moves along a horizontal line for 13 seconds. The first question is, what is the particle's acceleration at 4 seconds? The answer to this question is simple. All you need to do is look at when t is equal to 4 and find the slope at this point. Since acceleration is the double derivative of the position versus time graph, then the slope at 4 seconds would be equal to the acceleration when you were looking at the velocity versus time graph. Thus, the answer to this question is -1 meters per second squared, because when you look at the graph, at time is equal to 4 seconds, the slope of the line going through this point is -1. The next question is, what is the particle's velocity at 0 seconds? To solve this problem, all that you need to do is look at t is equal to 0. At this point, the y-axis, which shows velocity, is at 3. Thus, the answer to this question is 3 meters per second. The next question is, when is the particle speeding up? In order to determine when the particle is speeding up, you must look at both the acceleration and the velocity graphs, as discussed earlier. When the acceleration and the velocity have the same sign, then the particle is speeding up. But when acceleration and velocity have different signs, then the particle is slowing down. Using this knowledge, we can determine from 2.5 to 3 the particle is speeding up, as well as from 6 to 7, because both the acceleration and the velocity have the same sign. This is the final question regarding graphs that we will answer today. The question is, when is the particle moving forward? To answer this question, we must remember that velocity measures direction, but speed does not. Thus, we simply need to look at the velocity. When the graph of the derivative is above 0, then the particle is moving forward. Because of this, from 0 to 1, 2.5 to 4, and from 6 to 13, the particle is moving forward because the graph is above 0. Next, we will discuss an analytical usage for derivatives in order to find the velocity and particle motion at a certain point in time. Next, we will look at the values of a position of a moving body and its relationship to time. The first step of this problem is to plot s versus t and sketch a smooth curve through the given points. To do this, you must first create an xy axis. On the x-axis should be time in seconds, and on the y-axis should be the position. Next, simply plot the points onto the graph, using the above information. The first point would be 0, 5, the second point, 0.5, 12.5, and on. Then create a smooth curve of these points. The next question is, assuming that this smooth curve represents the motion of the body, estimate the velocity at t is equal to 2 seconds, t is equal to 3.5 seconds, and t is equal to 4 seconds. In order to do this, you must look at the two values surrounding the value at question. For example, at t is equal to 2 seconds, you would use 1.5 and 2.5 from the chart above. In order to do this, you use the equation s of b minus s of a over b minus a, with b being the larger value. Next, you simply plug in the values into the equation. Using the equation s of b minus s of a over b minus a, we can solve for the time at 2 seconds. At 2.5 seconds, the displacement has been 50.1 feet. At 1.5 seconds, the displacement has been 26.3 feet. b minus a, or 2.5 minus 1.5, is equal to 1. With this information, we can simply plug it into the equation and find that the estimated velocity at t is equal to 2 seconds is 23.8 feet per second. The question at hand is, the position of a particle moving in a straight line during a 10-second trip is shown by the equation of s of t is equal to t squared plus 5t plus 6. Include units in your answers. The first question is, what is the particle's displacement after 3 seconds? In order to solve this problem, you must use the equation s of the final time minus s of the initial time. Since the final time was 3 seconds and the initial time was 0 seconds, you would use the equation s of 3 minus s of 0. And since you know that the function for s is t squared plus 5t plus 6, then all you need to do is plug in 3 for s and 0 for s in the following order. Then simply reduce until you only have 2 numbers left. After combining, you will get the final answer of 24 centimeters. This means that the particle's displacement after 3 seconds was 24 centimeters. Next, we will solve for the particle's velocity at 3 seconds. In order to find the velocity at 3 seconds, all we need to do is take the derivative of s of t. First, take the derivative. The derivative of this function is equal to the velocity. The derivative of s of t is equal to 2t. Next, just plug in the value for t, which is 3 because it's 3 seconds, and this means that the particle's velocity at 3 seconds was 11 meters per second. Next, we will find the particle's acceleration at 3 seconds. In order to do this, we will simply take the second derivative of the original function. When we do this, we will get an answer of 2. This means that at 3 seconds, the acceleration is constant at 2 meters per second squared.